So intersections. So like of lines, you mean?
Yeah, I kind of just mean like, yeah, those things.
Yeah.
Lines.
So that's sort of like solving. Yeah, okay, so we can talk about that. That basically amounts to solving a system of equations, but by graphing. Yeah. So I could basically show you an example of that here. So maybe let's look at number 11 on this sheet. I'll write it up here on the board. So it's 5x plus 2y equals 16. And it's 6x plus 3y equals 21. Okay. And so the point of the problem, of course, is to solve this, but maybe let's try and do it. We have several different ways we could solve this equation. And maybe one way we could solve it would be by graphing these to see what it looks like. Maybe we could give that a shot and see what happens. And so it's going to be a little annoying. So maybe what I want to do actually. No, actually it won't be that bad. Okay. So here are our equations. I'm going to graph them, and we're going to look for an intersection point. This will have a solution if the two lines, one for each equation, if those two lines intersect somewhere in a point, and that'll represent my solution. So basically, let's just graph these. So this would be a nice review of graphing and also of solving a system. We could solve this by elimination or substitution, or you could make a matrix and do it that way, but let's graph, since that's what we're being asked to do. If I were going to graph this, there's maybe a couple different ways you could do it. You could either find 2 points and then draw the sort of connect the dots, or you could just kind of put it in the slope-intercept form and then use that to find your 2 points. Maybe what I'll go ahead and do is we'll put it in the slope-intercept form to show you how to use the slope to graph, because I think that's helpful to see. So let's take this first equation and put it in the slope-intercept form. I have 5x plus 2y equals 16. Again, the slope-intercept form, I'm just going to solve it for y, so that means 2y equals negative 5x plus 16, and then y equals negative 5 over 2x plus 8. Just divide both sides by 2, and I get this. Okay. So if I wanted to graph this line from this equation, I know the y-intercept is 8 because I'm in slope-intercept form. And so if the y-intercept's 8, that means my starting point is going to be 8 on the y-axis. So that's 8 tick marks. And I plot a point at 8 on the y-axis. That's where the y-intercept is. That's my starting point. And now I just need to find another point on the line so I can sort of connect the dots. And to do that, I'm going to use the slope. And the slope is negative 5 over 2. So that tells me that I should go to the right by 2, and then I should go down by 5, because it's negative. So we'll go to the right by 2, and then down by 5. So right by 2, and then 1, 2, 3, 4, 5. Right there is my next point. If I wanted to, I could find more points. I could keep going. I go to the right by 2 again, and then down by 5 again. 1, 2, 3, 4, 5, and so forth. I could keep finding points on this line. 2 is really enough. We'll connect the dots. And I drew it sort of not to scale, but there we go. As close to straight as I can get. So there's the first line. It should look something like this. Okay. We could do the same kind of thing with the other line. I'll do it in a different color, maybe. Blue or something. I don't know if it's really going to show up on the camera. If we do the other equation, what do I get? I have, if I solve the second equation for y, I'll have 3y equals negative 6x plus 21. And then divide everything by 3. I'll get y equals negative 2x plus 7. So with the second equation, the y-intercept is now 7. So I'll go to 7 on the y-axis. And then the slope is negative 2, which means when I go to the right by 1, I go down by 2. So it's to the right by 1, down by 2. The right by 1, down by 2. Right by 1, down by 2, and so forth. Yeah, there's something sort of off with my, I think this is supposed to be Okay, there we go. And then connect the dots. So technically, we only need 2 points to graph the lines. I like to maybe find more than 2 sometimes just to make my lines neater. But you only need to find 2 points on a line. Anyhow, I've now graphed both lines. So I have this black line and this blue line. And if we look, in spite of the fact that my drawing is a little sloppy, we'll notice that these 2 lines intersect in 1 point. They intersect right here. And so that point is supposed to represent a solution to this system of equations. So what do I mean explicitly? I mean this. I'll erase these. What are the coordinates of this point? It looks like it's about 2, 3. Now, I sort of eyeballed this. It looks like it's about 2, 3. And if we plug that in, that should work. You can check here, that should work by plugging in 2, 3. So this 2, 3, aka x equals 2, y equals 3, is our solution. This is it. Try taking these and plug them in up here, and they should solve both equations. Okay. So for intersecting lines and all that, the intersection of the 2 points represents a solution to the system of equations, where each equation represents one of the lines. If the 2 lines don't intersect at all, like if I had 2 parallel lines like this, then there's no solution at all because they don't intersect anywhere. On the other hand, if I graphed both equations, but they are just basically giving me the same line twice, so if it overlaps completely, then there's infinitely many solutions. So that's sort of how that works. So I don't know. That answer your question, I suppose. And anyone else have any other questions?
14, please.
14, okay. Let me just take a quick look. 14 is one of these. Okay. So this is a good question. I did something sort of like this on the board last week, and so this will be a good refresher. So 14 says I have the system of equations x plus 2y equals 6. And then the other equation is 3x plus ay. And that's equal to 2. So we have this mysterious a in the second equation. And we're supposed to...
Quick question. Is that
Yes.
supposed to be negative x?
Yes, thank you.
Okay.
Negative x. Yeah, thank you. So we have this mysterious a, and we're asked to find how many solutions have for a certain value of a, because they tell us that there is one value of a where there's not a unique solution. So we need to figure out how many solutions it has at that value. The point being that at that value, it'll either have no solutions or infinitely many solutions. That's what it means to not have a unique solution. So my advice on this kind of problem is to just try to solve it like we normally would, maybe with like the elimination method or something like that. A matrix would probably work too. But let's just try to solve this out and kind of just see what happens with a. And we should get to a point where it should be clear to us which value of a is going to sort of mess things up. So let's just try to solve this out. Let's say I was going to do the elimination method and I wanted to cancel out the x variable. What would I need to do? Well, I want the numbers here to be opposites. So I have negative x and 3. I should multiply the first equation by 3. So I'll get negative 3 plus 3 is 0. So let's multiply the first equation by 3. What do I get? I get negative 3x plus 6y equals 18. I'm going to add that to 3x plus ay equals 2. So I'm going to do this addition. So when I do this, the x's cancel, because I have 3 and negative 3. Here I'm going to get ay plus 6y, and then 18 plus 2 is 20. So, you know, I'm kind of being cheeky. I'm just going to add this to this. Well, let's just add them up. Now, we want to simplify that, though, to make some sense out of this. And what I would say is the magic word here is factor. Each of these terms has a y in common. They both have a y. So I can factor the y out, meaning that I can simplify this into this. Yeah, I can do this. A plus 6 times y, with parentheses, is the same as this, just factoring out the y. If you like, think about if you were to redistribute this y here using the distributive property, just distribute the y, I would get back to where I started. So this is really the same thing as this. Okay, and that's a useful trick. It'll come up sometimes in our class. Next chapter, that's going to come up again. We'll see where. Anyway, I have a plus 6 in parentheses times y equals 20. So where do I go from here? Well, I want a value of a where I won't get a specific solution. I won't get a unique solution. And so if this is not 0, if a plus 6 is not 0, then I could divide by it. And I could get y equals 20 over a plus 6, which means that I could solve for y. And then I would be able to find a unique solution because I know what y has to be. So the problem would be, there's a problem if a plus 6 equals 0. This is where things will be an issue, is if a plus 6 equals 0. Because if it's 0, then this left-hand side will be 0, and it will say 0 equals 20, which doesn't make any sense. Yeah, so we can't solve it out. So when does a plus 6 equal 0? Well, that's, of course, when a equals negative 6. So the magic value is a equals negative 6. And how many solutions do I have when a is negative 6? Well, plug in a is negative 6 here. What do you get? You get 0 equals 20. And of course, that doesn't make any sense. That's false. So there are no solutions when a is negative 6. Because when a is negative 6, I get nonsense. Okay. Cool. More questions? Can be about this problem or another problem.
Yeah, I'm just curious as to how you figured that. Let me see. Hold on. Sorry, it's loud here. I just forgot. Sorry. It'll come back to me. I'll let you know.
Yeah, no problem. Anyone else have a question?
Can we try one of the word problems?
Yes. Is there a specific one you want to see, or do you just want me to kind of pick one?
Nothing specific. I just have trouble sometimes translating the word problems into equations.
Yeah. Let's see. Let's maybe do. I think 15 is a good one. Let's look at 15. I can do that. So I'll erase this. So I'm not going to write the whole word problem up here because that'll take up a lot of room and time. So you guys should read number 15. I'll read it aloud here just so we know what I'm talking about. Number 15 says, I have a shop that has 2 types of sandwiches, large and small. To make a small sandwich, 5 inches of bread and 2 ounces of meat are required. To make a large sandwich, 7 inches of bread and 3 ounces of meat are required. If the store has 1,300 inches of bread and 550 ounces of meat, how many sandwiches of each type can they make so that all of the bread and meat are used? Okay. This is a good example of a word problem. It's pretty typical. And somehow it relates to stuff that we've talked about in this class. We'll see how. So whenever I do a word problem, my general strategy is this. I need to get an equation or equations that I can then solve, right? So I want to try to make up some equations that represent the situation that I can then just solve and then reinterpret the solution to that equation or system of equations in terms of the problem. So I need to get an equation. And if I want an equation, the first thing I need are variables. So I'm really looking for some variables first. And the variables should just represent something in this problem that I don't know, but that I want to know. So what do I not know that I would like to know? I need to know how many sandwiches of each type to make, right? That's what I don't know, but that I would like to know. So there are 2 types of sandwiches, so I should have 2 variables.